So, what really makes an engineer? It's not just about textbooks and exams, right? It's a journey of building things, watching them fail, and then learning from that. Today, we're going to take a look at a series of academic documents, reports, a thesis, and transform them into the story of one engineer's incredible journey. Let's dive in and see the blueprint of how an engineer is made. And his quote right here. It's from the engineer at the center of our story, Peng Ming. It just perfectly sets the stage. It's not about what you know, it's about what you do with what you know. That whole philosophy is the engine behind everything we're about to see. Now, to get a sense of who we're talking about, this isn't someone fresh out of college. Before going back for his master's, Peng Ming was already a quality assurance engineer at a major aerospace company. I mean, we're talking about the high-stakes world of aircraft manufacturing, a very serious job. So you might be asking, why would he leave a job like that to go back to school? Well, it's because he wanted to get his hands dirty, go deeper. He signed up for a master's program in space systems engineering. This wasn't just about adding a line to his resume. This was a mission to learn how to build the kind of complex systems he was truly passionate about. All right, so this is where the real adventure kicks off. And we're not going to treat these projects like homework. No, these were missions, each one a critical stepping stone to the next. First up, Mission GEOZONE. And the challenge? Just, design, build, and launch a high-altitude balloon to the edge of space to collect scientific data. For a student project, that is wildly ambitious. And look at these objectives. They were not messing around. They had to get ozone data way, way up there, snap some pictures of southern Taiwan, measure all the usual stuff like temperature and pressure, and then, and this is always the nail-biter, they had to get the whole thing back in one piece. This list of parts gives you a real sense of the complexity. I mean, this is not your kid's science fair volcano. You've got the main brain, the GPS for location, a bunch of different sensors, and this LoRa module, which is crucial for beaming all that data back to Earth. The trick is getting all these different pieces to talk to each other without freaking out. And this is what it's all about. You go from a pile of components on a desk to this, a flight-ready payload, all soldered by hand. Anyone can draw a diagram on a computer, but to actually sit there with a soldering iron, making every single connection, knowing this thing has to survive a trip to the stratosphere, that's engineering. Okay, so the big moment, how'd it go? This is always the fun part, where your beautiful computer models meet cold, hard reality. They were aiming for almost 36 kilometers up, but only made it to about 25. And then, check out that descent speed. Yeah, no parachute. It came down like a rock. This is a classic lesson. Your predictions get you in the ballpark, but the real world always throws a curveball. But here's the thing. The real results weren't the numbers it collected, they were the lessons they learned. So what worked? They got data back. That's a huge win. Temperature, pressure, it was transmitting. What didn't work? Well, the GPS conked out at high altitude, and the ozone sensors couldn't keep up. So this wasn't a failure at all. It was basically a perfect roadmap for what to do better on the next mission. All right, on to mission number 2, and you're going to see exactly how those lessons get put into practice. He's leveling up, big time, from a high-altitude balloon to a fire-spotting satellite. The question they're trying to answer with this next project is a really important one. How can you spot forest fires from space and do it fast enough to actually make a difference? With wildfires, early detection is absolutely everything, so the goal was to build a working model of a system that could do just that. And the system they came up with is actually pretty clever. It's a simple 3-step chain. Step 1, a sensor on the ground detects a fire. Think of it like a smoke detector for the forest. It sends out an alert. Step 2, the CubeSat flying overhead catches that alert. But it doesn't just pass it along. It adds its own data, like here's where I am and here's how my battery is doing. And then step 3, the CubeSat zaps that whole package down to a main ground station. Boom. Simple, smart, effective. And check this out. They built the whole system into what's called a 2U CubeSat model. A CubeSat is basically a standardized small satellite format, about the size of a loaf of bread. This is a huge leap from the styrofoam box they used for the balloon. You can see the progression here. They're working with professional, industry-standard hardware now. Okay, so we've seen him build these big, complex systems, right? The balloon, the satellite. Well, now the story takes a really interesting twist. For his master's thesis, he goes from this huge, zoomed-out view and zooms all the way in. He decides to master one single fundamental component.
And that component is the solenoid valve. Now, what is that? It's basically an electronic gate for fluids. You send it an electric pulse, and it opens or closes. And these things are everywhere. I mean, in your car, in factory robots, even on spacecraft. They're a basic building block of modern technology.
So here's the problem he decided to solve. Think about pushing open a really heavy door. You need a big shove to get it moving, right? But once it's open, you just need a tiny bit of pressure to hold it there. Solenoids are exactly like that. They need a big jolt of electricity to open, but way less power to just stay open. But most systems are kind of lazy. They just blast it with full power the entire time, which wastes a ton of energy. And this chart just says it all. Look at this. The old way of doing things was burning through over 16 watts of power. His new optimized circuit, just over 3 watts. That is an insane improvement. We're talking about an 80% drop in power use. It just goes to show you, sometimes the biggest breakthroughs come from obsessing over the smallest details. So let's zoom back out. We've gone from the stratosphere to low Earth orbit and down to a tiny little valve. So what does it all add up to? Well, what we have is the blueprint for how you forge a modern systems engineer. You can see how all the pieces fit together, right? That balloon mission, that taught him how to deal with failure and learn from messy, real-world results. Then the satellite mission taught him how to juggle a bunch of complex parts and make them work together. And finally, his thesis. That taught him the power of going deep, of focusing on one tiny thing and optimizing the heck out of it. It's this amazing progression from the big picture to the small details to mastery. And it all kind of leads to this one big question, doesn't it? What is an engineering education really for? His journey shows us it's not about getting a good grade on a test. It's about having the guts to build something in the first place, the resilience to watch it fail, and the wisdom to figure out why and build it better the next time. That's the real skill.